Good morning. We are ready to move on. Congratulations, you've made it through all of thermodynamics, the first 4 weeks of the course, and now we are prepared to move on to something entirely new. So you can forget all of thermodynamics until the final exam, and then you have to remember all of thermodynamics. But for the next 12 weeks, for the rest of the semester, we're going to be looking at electric forces and magnetic forces, electric and magnetic fields, and then we're going to switch back and forth between looking at the electric and magnetic force stuff with direct DC and AC circuits. So a lot of really interesting stuff ahead. So let's go ahead and get started. Kind of our starting point for looking at the electric force is in chapter 21, and it's looking at introducing the idea of electric charge and electric fields. So, and electric force, they left that out in the title. So I'm going to say electric charge, electric force, electric field. And there's a lot of stuff that they packed into chapter 21. It's one of those chapters that maybe has too much stuff in it. So anyway, let's go ahead and get started. So as usual, I'm going to skip through the list of topics pretty quickly. If that's useful, and I'm going to leave it in there because I know that sometimes it's useful to be able to just kind of check things off. But anyway, I'm going to move on. The chapter starts out looking at what we refer to as static electricity. Now this is something that we see in kind of everyday life. This picture we had back here was an example of static electricity. You know, with everyday kind of objects, there are ways to charge different materials and then see these forces show up. You know, taking clothes out of a dryer, for example, all the clothes stick together. Why is that? And it turns out that charges, in most cases electrons, are actually, we're able to transfer those back and forth from the surfaces of different materials. And if we transfer back and forth just a small portion of the electrons, we can see some pretty large forces show up from that. So here it's saying that objects can be charged just by rubbing objects or making some kind of mechanical interaction between the charges can actually transfer some electrons. Electrons can get transferred. Now, when we look at electric and magnetic forces, we have to think in terms of the protons and the electrons that make up those objects. The protons, as I'm hoping you all know, are positively charged. Electrons are negatively charged, and so protons and electrons interact through the electric force. Now, I put neutrons in here. It seems funny to bring neutrons in when we're thinking of electric forces. After all, neutrons are electrically neutral. But even though neutrons are electrically neutral, they experience magnetic effects. It's a little weird. Turns out that protons and neutrons are not fundamental particles in the way that electrons are. So protons and neutrons are made up of what we call quarks, and the quarks are electrically charged. Now in the proton, if we add up the charges of the quarks, the constituent quarks that make up a proton, they add up to one full unit of positive charge. In the neutron, when we add up all the individual charges, they add up to 0. So in the neutrons, even though the electrical charges cancel out to 0, which makes a neutron electrically neutral, it still has charges that are moving, which create magnetic effects, and that means that the neutrons respond to a magnetic field. So anyway, just kind of an interesting thing, I hope, to toss in there. So we're going to primarily concern ourselves with counting protons and counting electrons. Now, as we mentioned, in most materials that we're kind of familiar with, it's the electrons that are moving around. Protons are built into the nuclei of the material. And for the most part, the nuclei are embedded in some kind of electron lattice and are not very mobile. But a few of the electrons, in an atom or a molecule, some of the electrons can separate, or a few extra electrons can come in. So typically it's the electrons that are mobile. So in this example, they rubbed, I don't know if this is a wooden stick or what, but they're showing that by rubbing these objects, we can actually create, we can end up with some extra electrons, which make the object negative, or we can end up with a depletion of electrons, which leaves the object positively charged. And then other objects can acquire these charges, and you can end up with these attractive forces. So there's a number of these slides showing some of these examples, and I'm going to go through these pretty quickly. They're interesting to think about, but we've got other sorts of problems to take a look at. So anyway, let me talk through some of these. And so this slide is saying that the charges come in two types. Those have been classified as positive and negative. So we have these positive and negative charges. Charges with the same sign repel, and charges with opposite signs attract. So two negatively charged objects will push away from each other. Two positively charged objects will also push away from each other. There will be repulsive forces between those objects. If we have negative and positive charges, they actually attract. So I'm guessing most of you, this is probably pretty familiar. Now, let's think, why is that happening? And it comes down to protons and electrons. So when we have an object that's positively charged, what we're saying is that, hey, this positive charged material, some of the electrons have been removed, and that's what's making it positive. Now, protons, which are positive, push away from each other. Electrons, which are negative, push away from each other. So that's the idea of, if you have objects with the same charge, they will repel. But a proton and electron will attract each other. And it turns out that the forces pushing two electrons away from each other, the forces pushing two protons away from each other, are the same amount of force. And the amount of force pulling a proton and an electron together, that's also the same magnitude force, although it's attractive instead of repulsive. And we'll see more of why that is, or how we understand that to be the case. So again, I added in here the electrons are able to move around for many materials. And so we typically think of the electrons as either there's a depletion of electrons in a positively charged object, or there's an excess of electrons in a negatively charged object. So here we're saying that electric charge is conserved, and so we can actually trace that principle down to the fact that the number of protons and the number of electrons are conserved mostly. When we get into physics 4c, we'll see some reactions where actually protons and electrons aren't conserved. Protons can be turned into neutrons. That's kind of interesting. Electrons can be turned into what we call neutrinos. But for the most part, for 99.999% of the situations that we're going to be looking at, the number of protons and the number of electrons are conserved. And that's the basis for electric charge conservation. Even in the cases where protons turn into neutrons, and even in those cases, overall charge is conserved. So electric charge conservation is going to be a fundamental principle that we'll continue to work from. Now, what they're pointing out here is that within the atom, they're just kind of giving us an idea of how are charges arranged. What's the configuration of arrangements of charges in atoms and molecules? Because that's the basis for all of the electric forces that we're going to be looking at. And what they're pointing out is the nucleus is small, It's got a lot of mass, and it's got a positive charge. Now, let's take a look at those properties. First of all, the nucleus is really small. If you think of the so-called size of an atom, when we talk about the size of an atom or a molecule, that's pretty much what we're talking about is the distribution of electrons. Electrons are big and take up a lot of space. Now, this is kind of bordering, we have to talk a little bit about particle properties. We have to get away from the idea that the electrons and protons are little marbles, little tiny objects. You know, this picture shows an electron orbiting. That's not an accurate picture of the properties of an electron. Individual electrons have a probability of being in many different locations at any given time. So we have to think of electrons as forming kind of a probability cloud. If you've taken chemistry classes or other physical science classes, you've certainly run into this, where you talk about electrons as not existing at just one point, certainly not following some kind of an orbit, but rather as a distribution of probability as to where the electron is. So again, this picture is a little misleading, or very misleading, because the individual electrons are filling some kind of space. And in an atom or molecule, the electron cloud takes up, you know, almost all of the space. The nucleus is tiny, 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 tiny. If we did this picture to scale, the nucleus would be a little tiny speck. If we had an atom the size that's shown in this diagram, the nucleus would just be a little tiny speck at the center. Okay. Now, what's interesting of this, and then we say, well, where's the mass? Well, the proton is 1,800 times more mass than an electron. So even though the nucleus is super tiny, taking up a tiny, tiny fraction of the volume of an atom or molecule, it's got, you know, 99.95%, something like that, percent of the mass. Almost all the mass is in the nucleus. So atoms and molecules are kind of interesting because a nucleus we think of as a point object. And since we're starting to look at electric charge, we're going to think of the nucleus as what we call a point charge. It's both a point mass and a point charge. It's an object with mass and charge that effectively is so tiny, we can treat it as if it's located at just one location. Okay. Now, the electrons, on the other hand, are, you know, big and bulky and take up all this space. So those have to be thought of as a charge distribution or a mass distribution. Now, what I always think is funny with this word massive now is, you know, over the past, especially I'm going to say the past 10 years, more and more people say, when they use the word massive, what do they mean? And they don't mean that it has a lot of mass. They mean that it's really big. So that's a problem. So you've got to, you know, as a scientist, as an engineer, you got to keep reminding yourself that when most people say the word massive, they mean it's really big. But massive really means, in science and engineering, that it has a lot of mass. And so the nucleus, again, contains an enormous amount of mass, but it's really tiny. Okay, so it's massive, but tiny. And it's positively charged. And then the electron cloud, this distribution of electrons, is negatively charged. So you always want to work from that model. You know, we're constantly referring to atoms and molecules and their properties, and you want to keep reminding yourself that's how I need to think about atoms and molecules. All right, here's a water molecule. Now, electric charges are a little complicated. When we think of these atoms, like this, again, what's happening is I have a point charge of the nucleus that's positively charged, and then I have this cloud of electrons. When we apply that to a molecule, like water, what's going on in this water molecule is I have an oxygen nucleus, which is a positive point charge. I have a hydrogen nucleus, which is a positive point charge, and another hydrogen nucleus, positive point charge. And then we have electrons that are kind of spread out. So when I look at this green sphere and these red spheres, that's referring to the electron distribution. Okay. So when we say the atoms are this shape, it's really the electrons that are determining that shape. The nuclei are these little tiny points embedded within these electron distributions. So there's going to be a bond length. The distance, the internuclear distance between the oxygen and the hydrogen, it's a bond length. In chemistry, that's what we'd call it. In physics, we'd call it the same thing. But it turns out that the electron, the shapes of the electron cloud, is a moving target. There's not one fixed shape that the electrons have to conform to. And so in a water molecule like this, if it's isolated, what happens is the electrons have what are called quantum states, which we'll look at in a good amount of detail in Physics 4C. I know I keep advertising Physics 4C here. So we get to go in and use quantum mechanics to understand what different shapes the electrons can have. Each quantum state for the electron corresponds to a little different shape. Now, what happens as a result is the electrons don't necessarily distribute themselves in a way where they uniformly surround the nucleus. The electrons can tend to favor certain nuclei over other nuclei. Within the water molecule, water is a great example because everybody's familiar with water and you've probably been talking about water properties since kindergarten. So you've had a series of instructions in your science classes and about how water and its properties. It turns out that because of quantum mechanics, because of the ways an electron can arrange itself around the nuclei, electrons tend to have higher probabilities at the oxygen end of the molecule more so than the hydrogen. The electrons actually get pulled away from the hydrogen nuclei and they get drawn more so towards the oxygen nucleus, and that makes the water molecule charged. You would think, well wait, I got protons, electrons, shouldn't the atoms be neutral? And you think, no, turns out not. Turns out that atoms and molecules have little regions of positive and negative charge to them, and that complicates them. If you've taken chemistry classes, you know that in chemistry they talk about the chemical bonds. That's kind of the starting point. But then they introduce kind of this stickiness between molecules. Maybe they call it hydrogen bonding, or they call it London dispersion forces. These other forces that they talk about, and that we're going to be talking about, have to do with these little leftover charges that are still there even once the molecule has formed. So once the electrons have found themselves in certain quantum states, that's kind of the bulk of what's going on. But then there's these leftover positive and negative charges that continue to play a role in how molecules interact. You guys probably know water molecules tend to stick to other water molecules pretty well. And that's because water molecules have more of this polar effect, it's referred to as a polar molecule, than typical molecules. More so than average, water has these polar properties to it. And it's important because it means that at Earth temperatures, for example, water is a liquid. If it didn't have these leftover positive and negative charges, which tend to attract other water molecules, water would be a vapor, which would very much change certainly the development of life on Earth, as an example. All right, so the polar molecule thing, I think that's huge. If you guys are going to be scientists or engineers, so much depends on the properties of materials, properties of different compounds like water, and so it always traces back to the positive and negative charges. It's all done with these little leftover positive and negative charges. Couple quick items here. It talks about insulators and conductors. It says that here we have two objects. One has been charged, so it's missing some electrons. It's positively charged. This one is neutral, so this one has the same number of electrons and protons currently. Now, in the case of, if we take a piece of metal and place it on these two objects, that will enable the positive charges, to transfer to the other object. Now, when the positive charges transfer, what's really going on in most cases is the electrons that were here have now transferred to the other side. Electrons from here have transferred over and eliminated some of the excess positive charge. Meanwhile, since the electrons have transferred, they're leaving a positive charge on the other material. Wood, they point out over here, actually tends to be an insulator and is not going to be able to transfer those charges the same way. Okay. Now, it turns out it's a little more complicated than this. Static electricity is a fairly complicated process. Many insulators can also acquire some kind of a surface charge, so they can support extra electrons primarily as a surface effect. It's not conduction through the material, but this is fine for us. The idea of insulators and conductors following these rules. Now, with objects, you can take something that's neutral, and if you bring something that's positive nearby, you can actually, they're saying this is metal, so it's a conductor. You can get some of the electrons to transfer over, and you can charge things by getting the electrons to transfer. Now, here's a trick. What we can do is take something that is electrically neutral. It's currently grounded. That little symbol over there with the three lines, that's a grounding symbol. Now, ground means that the object is connected to something that can serve as kind of a reservoir of electrons. So, for example, if you have housing, wiring in a house, there is a ground that is placed at each electric box for a house. There's a line that runs out. There's a big copper tubing piece that is pounded into the ground. That means that that box is electrically connected to the ground by a very good conductor. And the idea is to prevent any accumulation of charge on the wiring of a house. So that grounds it to the earth. Even though, the earth is not a super good conductor, you can certainly, it's such a large object that it can provide electrons or remove electrons as needed to prevent any kind of a buildup. Recently, I put my wife and I put solar panels on our house, and we had to upgrade our electric box. And so the person doing the electric box came, and I said, we already have a ground, and he goes, oh no, the code now is to have a much more thorough and complete grounding. And he had this long copper cylinder that was it was like 2 meters in length, and he had a little portable jackhammer, and he put that next to the ground, and he reached up with this portable jackhammer and pounded this thing all the way down into the ground and connected it to that. So it was a pretty serious grounding effect. Anyway, so that's what that ground symbol is showing. This object is neutral, and it's been connected to Earth, for example, as a way to stabilize having no charge. Now, what we're going to do with the metal rod here is that this thing's going to come in as negatively charged, and what happens now with the with this other object here is that we can actually transfer charge through a grounded device. Now, If we remove the ground, then what we're going to be able to do is store up some of the positive charge in this device. So we can have this drawn nearby. This end becomes positive. Some of that negative charge transfers out through the ground, then we cut the ground, and we've actually charged that object. Now this is an effect called induction, because we don't directly have to make contact between these two devices. It's enough to bring this object nearby. That's enough to separate the charges in the metal conductor. So it's another example of it's a moving target. These electrons are mobile, and that means that they can move around, and we can play these different kind of tricks where I bring something in, this end becomes negatively charged, this end becomes positively charged. Okay. So you can't tell the electrons what to do. The electrons are going to move around depending on what gets brought in. Now here's another interesting example. Here's a non-conductor or an insulator. And now I'm bringing a positively charged device into it. Even though the electrons in an insulator are not moving, they're not able to move around freely, the molecules themselves will polarize. Remember we talked about water as an example of a polar molecule. And so the material in here will polarize, which means in this example, the electrons get drawn a little bit in one direction and the nuclei get pushed away. You're stretching out the molecules a little bit. And that creates an effect within the material where this end of the material has a measurable negative charge to it, and the other side of the material has a measurable positive charge. So insulators, as well as conductors, the charges are moving around. It's possible to reconfigure the charges. Here's kind of a fun device. We've got these in the lab. Our first lab in this section on electric forces, we're going to look at something kind of similar to this. We've got a couple of, it's gold. We don't have any gold in the lab. But these leaves are made out of gold. And what it does is it lets us make the leaves really thin. Gold, it turns out, has excellent properties of malleability. You can make the leaves really thin so they don't have much mass. And then what you can do is you can put a little bit of charge onto this. If we now bring in a positively charged object, for example, we can cause this is induction. We haven't made contact yet. But what we have done is we've created a negative, the electrons are being pulled towards this end, towards this spherical end of this, and that leaves a depletion of electrons in the gold foil. And positives repel each other, so we can see this effect as the gold foil pushes away. We didn't have to make contact. We did this through an induction effect. Now this is through conduction, so if you actually make contact, then the electrons now have jumped into this positively charged material. And again, we see the effect of this is now, the two foil pieces are positively charged. And we can measure this effect by how far they push away. All right, we are ready to do some formulas for this. Let's see what kind of mathematical formulas we can come up with. Now, what I'm going to call this the electric force. I think it's, rather than naming it after somebody, I'm going to call it the electric force. It's officially known as Coulomb's law. And what we find through experimentation is that the electric force depends on distance between the two charges. It depends on how much charge the two objects have. So here's the two objects that are charged. We're going to use Q1 and Q2 to measure the amount of electric charge. Now I always feel like it's too soon maybe, right? You guys have spent 4 weeks learning that Q is heat. And now all of a sudden, again we said you can forget all of thermodynamics for right now, I guess. Q now represents electric charge. So, you know, throw that Q as heat out of your memory and replace it with Q1 is the electric charge of object 1. Q2 is the electric charge of object 2. They happen to be separated by a distance. Okay, so this is also hard. We've done this before. That little r means distance. And it's hard to get out that radius idea. So you have to say it out loud. Every time you see this formula, you tell yourself r is distance, center to center between the two charged objects. R is a distance, R is a distance. Now, the formula we're going to come up with, Coulomb's law, or the electric force, is going to be exact as long as the two charges are not moving relative to each other. So as long as the two charges are not moving, we can treat them as if they're both at rest. We'll develop formulas for that. But what I want you guys to be thinking, I don't want to throw this on, at you later on. I want you to be prepared. It turns out that the electric force, and magnetic forces too, are not just dependent on the charge and the distance. They also depend on how fast the charges are moving, and they depend on what the acceleration is of the charges. So I wrote those in. I added those to this slide just to let you guys know. If we want to know the full effect of the electric force and magnetic forces between two charged objects, we have to know their charges, we have to know their distance, and we have to know the direction and magnitude of their velocities and their accelerations. So it gets a little complicated, I have to admit. It gets a bit challenging, but it's also a pretty interesting force. Electric and magnetic forces are pretty interesting. So we'll see this, and we have 12 weeks to explore and discover what's going on with these electric and magnetic forces. Now, I'm going to be drawing a lot of connections to gravity. You guys are gravitational force experts because you successfully completed Physics 4A, right? So this looks very much like the gravitational force, except that with gravity, this was mass 1 and this was mass 2. Now, you have to ask yourself then, for gravitational forces, did those depend on velocities and accelerations? And it turns out they do, but we never talked about it. Okay, so we used a fairly basic kind of idealized model of gravity, where we said that the objects, they're never moving that fast, and so we don't have to take velocities and accelerations into account. So the gravitational force we looked at was just kind of the simple, basic version. Okay, now here is the electric force formula, and I'm hoping each and every one of you is saying to yourself, oh my gosh, that was just like the gravitational force, right? That's the first thing that went through your head when you looked at this. Because the gravitational force was, hey, gravity force is gravitational force constant times m1 times m2 divided by distance squared. Now, the electric force, it turns out, also is the force is equal to some kind of a force constant. Now, K, I'm going to say, is our electric force constant. It turns out that it's not just the electric force constant, it's also the magnetic force constant. And it turns out that electric and magnetic forces are part of the same thing. It's the same package. So, and for convenience, we separate it into electric effects and magnetic effects, but it's all part of one combined package. And we're going to start off by looking at what we call the electric components of force. So K is the electric force constant, R is the distance, and Q, I still think it's too soon, but is going to be the electric charge for the objects. Now, I wrote that in parentheses over there. This formula works exactly when the charges are not in motion. Okay, and we'll see some of the effects in later chapters. What happens if charges are moving? What are the forces going to be like? We'll look at that. So this equation gives us the magnitude of the forces acting between two charges. Okay, that's not such a bad formula to work with, right? And again, it matches up exactly with our gravitational force. The formulas look exactly the same. Okay, in fact, I even did another slide of my own here. So here's gravitational force, big G, m1, m2 over distance squared. Here's the electric force, little k, q1, q2 over distance squared. Gravitational forces, well, let's think about the differences. Gravitational forces are always attractive, right? So the force was always attractive. Now, the magnitude of the force acting on the two objects is the same. So the force that object 1 experiences and the force that object 2 experiences, those are the same magnitude when we looked at gravity. Now, with the electric force, as you guys probably already know, it's more complicated. If I have two positive charges, which we're going to use as kind of our default to think about the formulas. If I have two positive charges, the forces are going to be repulsive. If I have two negative charges, the forces are going to be repulsive. If it's a mix, if I have positive negative or negative positive, the forces will be attractive. Now, we didn't have that complication with gravity. So that's something we always have to look at. Every problem we look at, when we look at the charges, we have to write down in our diagram which of these charges are positive, which ones are negative, so we can get the direction of the forces correct. Now, the magnitude of the forces will come from just plugging into these formulas, kind of ignoring the signs of Q1 and Q2. We'll see how that works. Now, what I wanted to do also on this page was do a quick comparison of force constants. The gravitational force constant, 6.67, 10 to the minus 11 newtons meter squared per kilogram squared. That is a tiny number, right? So what that's telling us is, for ordinary everyday objects that are maybe a couple kilograms, if I have a kilogram object here and a kilogram object here, which we do, scattered around the room, there's not much of a gravitational attraction between them. It's so small, we just ignore it. If I have a textbook over here and another textbook sitting over here, we can calculate the gravitational force between them, and we find out that it's this tiny, tiny, tiny fraction, it's like a trillionth of a Newton or something, between those two everyday objects. Okay, so kind of negligible. The electric force constant, the value on that is 8.99 10 to the 9th. So that's like 9 times 10, 9 billion newtons of force per coulomb. Now the units here of electric charge, the big C right there, is called a coulomb, and that's the same coulomb that was in Coulomb force. It's named after somebody, and that's a measure of electric charge. It turns out 1 coulomb is a lot of charge. It's very difficult to get an entire coulomb of charge on everyday objects. We'll see this as we look at more examples. Anyway, I just want to point out that the force constant here is like 20 orders of magnitude larger. So electric and magnetic forces tend to be enormous compared with gravitational forces, at least at the level of atoms and molecules. So the forces holding atoms and molecules together are so large that they tend not to separate. Positive and negative charges, protons and electrons, tend to find each other and form stable, neutral atoms and molecules, and then they really don't rearrange themselves unless we run a chemical reaction or something. So these really large forces are on a tiny scale holding all the atoms and molecules together. All right, so a comparison of the forces and what's going on. So, look, I overwrote some of these things. I wanted to go back and say this is an electric force. So the forces here, same thing we were talking about on the previous diagram. If it's both positive, they repel. If they're both negative, they repel. If they are two opposite charges, they'll attract. Now, here's an extra complication that the textbook introduces, which I'm going to say you don't need to deal with. You can avoid this. They define what's called F12 and F21. Now, F12 and F21 have the same magnitude. So I don't think there's any need to pay special attention to the notation. What they've done is they've said, okay, the two magnitudes are the same, so each object will experience the same amount of force, but they're going to be oppositely directed. So the only real difference between F12 vector and F21 vector is the direction. Well, it's much easier to just not think of these as vectors, but instead think of this as, to separate the two effects, think of the magnitude separate from the vectors. So once I see that I have two positive charges, for example, in my diagram, I'll draw the two arrows to show the direction of the force. That takes care of the direction. Once the diagram has taken care of the directional information, then the only thing left to do is solve the magnitude. And the magnitudes are the same. So there's no need to keep track of, are the subscripts 1, 2, or are they 2, 1? Use the diagram to keep track of directions, and then F12 and F21 become the same amount, the same magnitude. Okay, one more of these slides here. Electric force, unit of charge is called a coulomb. The symbol we use is a big C. The proportionality constant, the force constant, 8.99, 10 to the 9th newtons, meters squared per coulomb squared. I'm going to include that number and write it out explicitly in a lot of examples because you want to get used to that number. That little k is going to show up in every calculation pretty much that we do dealing with electric forces, electric fields, magnetic forces, magnetic fields for the next 12 weeks. Okay? So, 7 weeks from now, you don't want to be thinking, what's that little k in my formula? Because it's going to be in every formula we look at. Charges, typical amounts of charge, they're saying, like static electricity, might be a millionth of a coulomb. So again, the way coulombs were defined was in terms of current flow in electric circuits. When we have electric circuits with current flowing through them, with electrons moving, we can move a lot of electrons. And so coulombs was a sensible way to define that. But when we have static electricity going on, it's unusual to accumulate a lot of charge in one location. And so most of these static charges that we talk about are going to be in the micro or the nano or the pico coulombs. They tend to be really tiny amounts of charge. All right, one piece of what I'm going to call historical baggage that we have to be aware of is this. The textbook has gone through and defined the electric force, and I think very sensibly, in terms of this diagram, in terms of this formula, with this force constant. And I wholeheartedly agree with that approach. But historically, let me say a few things here. Instead of calling it the electric force, the tradition is to call this Coulomb's law, okay, which I don't prefer, but you've got to be ready for that. So that's what it's going to get called. People are going to refer to it as Coulomb's law. I think when I look at the newer textbooks coming out right now, newer editions, I see this used more and more, but for better or worse, this historical baggage is still around. Also, historically, the formula was not written in terms of one simple force constant. Instead, it was defined in this thing called the permittivity of free space. Anyway, I think it's unfortunate that we still work in terms of this, but we do, so you've got to be ready for this. In fact, our textbook does this. Our textbook starts out defining this and does some examples, which I think is excellent. But then the textbook reverts back to the more established historical approach, which again, you got to be familiar with. So this permittivity is equivalent to 1 over 4 pi k, or k that we're working with is 1 over 4 pi epsilon naught. The force then looks like this, and the value of epsilon naught, 8.85, 10 to the minus 12 coulombs per newton per meter squared. Now, I'm going to exclusively use this, because I think that's a more useful approach to understanding how electric and magnetic forces are all related. I think this approach is less obvious. In any case, from time to time, I'll refer back to this, and you're certainly going to see this in the textbook. Okay, and you're welcome to use either approach you want to use. So I apologize for that fact that we've got kind of these two competing electric force constants to deal with. Just to give us some perspective as to, how many coulombs are, what's a fundamental charge? So if we took an object and we looked to see where the charges are originating from, it would come down to counting electrons and protons. The overall charge of any object comes down to counting how many protons we have, how many electrons we have, and then taking the difference. Now, each individual electron and each individual proton has this fundamental charge, and I should have written fundamental charge here, I didn't. If I was going back and editing now, I'd add that in. That fundamental charge is 1.60, 10 to the minus 19 coulombs. That's a very important number for us. So that electric force constant, little k, which again, that's too soon too, right? Talking about too soon here. Little k for 4 weeks was what? It was Boltzmann's constant. So whenever we're doing a thermodynamics problem, little k is Boltzmann's constant. But now little k is the electric force constant. Okay. We ran out of letters. I apologize. All right. So the electric charge, this fundamental unit, is the basis for all the electric charges that we measure in every object. It's going to be some multiple of that number. Now notice here that they said that this is the charge on a proton or an electron, but that's not quite true. A proton's charge would be positive, and the electron's charge would be negative. Now, in most situations, the negative and positive is going to be taken care of by the diagrams. Remember, we talked about keeping track of direction of force using a diagram, and then just calculating the magnitudes of the charges. So often that's going to be the case. Even though it's an electron, we're not going to necessarily include the negative charge in our calculation. And again, we'll see examples of that. All right, here is our next slide. And this one's just a reminder of something we've already looked at. It's saying that the proportionality constant, little k, which we've been using for the electric magnetic force constant, could be written in terms of epsilon naught. This, what I'm going to claim is kind of historical baggage, the permittivity of free space. Now that we have a better understanding of how electric forces operate, electric forces and electric fields, going back to the force constant k probably simplifies things. In this class, I'm going to be using little k for everything, but you do need to be aware of the epsilon naught because it's going to show up in your other classes. You could see either one of these constants used for electric forces and electric fields. All right, so let's look at our first example here. It says that we've got two charges. One of the charges is 50 microcoulombs, and another charge here is 1 microcoulomb. So charge 1 is, 50 times bigger than charge 2. And they're separated by some distance. Now here they're calling it L, and I think a better representation of this, the L actually should be from center to center of the charged objects. So it's not edge to edge of the objects. Centering that distance is a better representation. What we're assuming is that the charge is kind of uniformly distributed over this object. Same thing over here. Really should be center to center. So it says there's a distance L. Now we've been using little r for that, but in this case they've used L. And what they're asking here is, what are the forces that are acting on these charges? Now, as a result of the presence of the charges, each one of these charges will experience a force. So charge 1 will be experiencing a force due to the presence of charge 2. Similarly for charge 2, that's going to experience a force due to the presence of charge 1. A lot of times I like to refer to this as an interaction. So I have two objects, they're both charged. There will be an electric interaction between the two, and that's going to result in each of them experiencing a force. So here's my write-up for this example 21.1. Now I've gone back to using little r. I want to go back with the notation that the textbook first introduced. Here are the two charges, Q1 and Q2. And notice in my diagram, I've identified that both charges are positive, and that means that the electric force will be directed away. The force on each of these objects will be repulsive, and it will be exactly opposite the direction of the other charge. Now, when we get farther into electric and magnetic forces, it's not always this simple. It's easy to kind of get lulled into this idea that the forces are always either directly attractive or directly repulsive. That turns out not to be the case. It does get more complicated, but in this case where we have two objects at rest, or at least moving slowly enough that velocity effects don't come into play, the force is going to be directed exactly opposite. That's what we're going to be seeing for the next several chapters. All right, I've written down the two charge quantities, 50 microcoulombs and 1 microcoulomb. And those microcoulombs are a reminder that it's unusual to have an entire coulomb of charge show up on just one object. That doesn't really, we tend not to get an entire coulomb concentrated in one location. Here's the force equation, which I'm going to claim is written in the easy format, where we're using the electromagnetic force constant, little k. And I've written that down, 8.99 10 to the 9th newtons meters squared per coulomb squared. I wrote in the 50 times 10 to the minus 6 coulombs for microcoulombs, 1 times 10 to the minus 6. And the distance between them is 20 centimeters. So I'm going to put that into standard units. This is one of those equations. I'm going to say pretty much all of the equations we're going to start running into now. It's easiest to work in standard units. We're starting to introduce more and more units. We'll see that happen over the next few chapters. And so sticking with standard units is going to be the easiest way to check and verify that the units are canceling out properly. So I put that into meters. Meters will cancel meters, coulombs cancel coulombs. I'm going to be left with a force in terms of newtons. Now just a reminder, you can never write this down often enough, R means distance. It's easy to fall into that idea that when you see a little r, you think radius. That's not what's going on here. It's distance, and it's center to center distance. The little f here, without the vector sign, the f, sorry, the capital F, here, here, here. Once we've solved for the force, both of these objects experience the same amount of force. So there's only one item to solve for here, not two. I can solve for this amount and this amount just once. Now the directional information is coming from the diagram. If one of these had been negative, let's say one of the charges is negative, one is positive, then the forces would have been attractive. They would have been directly towards each other, the two charged force directions. But in this case, it's repulsive. So what I calculated here, 11.2 newtons, that is a decimal, it's not a comma. So, run through these, check these examples that you see in lecture. If you find errors in them, let me know right away and I can get to those corrected and get the message out if there are numbers that don't match. And here's just a reminder that when I put those vertical lines on either side of a vector, I'm referring to the magnitude. So that's it. That's what one of these examples looks like. Here's kind of the simplest example of calculating a force acting between two charges. But these things get complicated pretty quickly. So let's try another example here. This time I have three charges. One of these charges is positive. Q2 is positive. It's 3 microcoulombs. But charge 1 and charge 3, they're negative. And they're -8 microcoulombs and -4 microcoulombs. Now, fortunately, all three charges line right up. I can draw an x-axis between all three. And that means that all of the forces I'm looking at for each of these charges is going to be lined up right along the x-axis. So it's a one-dimensional problem. I don't have to think in terms of the y direction or the z direction. Everything's in the x direction so far. I know you realize we're going to be moving into more dimensions here, but for this problem, everything's just along that one line. Now, what's going to happen here is, let's look at object number 1. Object number 1 is experiencing two forces. Object number 1 experiences a force due to the presence of charge 2. It also feels a force due to the presence of charge 3. Now, the presence of charge 2 is pulling charge 1 to the right. The presence of charge 3 is pushing charge 1 to the left. And the net force acting on charge 1 is going to depend, the direction of that force will depend on which force is larger. So again, charge 1 has two forces acting on it, and they're in opposite directions. Charge 2 also has two forces acting on it. Charge 3 is pulling it to the right, charge 1 is pulling it to the left. We have to do a calculation to find out which force is larger and to find out what the net force would be. Finally, charge 3 is going to be attracted towards charge 2 and pushed away from charge 1. So each of these three objects, if we look at them individually, has two forces acting on it due to the presence of the other two charges. And what they've done in this problem is, you could imagine a problem where they ask us to solve for all three objects. But they only ask us to solve for one object. They said, okay, it's a lot to ask to do all three, just do object 3. What are the forces acting on object 3? Now, we already said that object 3 is going to get pushed away due to the presence of charge 1, and it's going to get drawn in towards object 2. So here's its force diagram. We've isolated object 3. I hope these words are familiar from Physics 4a. This in many ways, is, I'm guessing, is going to feel a lot more like things we did in Physics 4a than thermodynamics did. Thermodynamics was kind of out there on its own in many ways. This is getting back to force diagrams. Okay. Thermodynamics, we did kinetic energies and velocities and such, but we didn't do very many force diagrams. And this is now, these electric forces are taking us back to vector addition using force diagrams. And I hope those are wonderful words that you want to hear and that they're not discouraging. That, oh no, force diagrams, you want to be thinking, yes, force diagrams. I love those force diagrams. So anyway, this is the force diagram for object number 3. What I need to calculate now is I need to find out how large is force acting between objects 1 and 3, and how large is the force acting between objects 2 and 3. Let's do that. So here it is. It's the same diagram. Now, I went in and I from the diagram, I looked at the distances. The distances are different. So these forces that we're going to calculate, here's the formula I'm using. That's my electric force formula. For each of these interactions, I need to be able to identify the charges and the distances. So that's what I've done. I've written down, now notice, I'm using on the diagram, I've already identified the direction of the forces by looking at positive and negative signs. Once that's done, I don't need to deal with plus and minus signs on my charges. So what I did was I just came in and I said, look, I'm going to just look at the magnitudes of the charges and calculate my forces from that. So for the force acting between objects 1 and 3, I was able to use the force formula to determine that was 1.15 Newton. And for the forces acting between objects 2 and 3, I identified that force as 2.70 newtons. Now, looking at my diagram here, I can see that the 1.15 and the 2.70 are in opposite directions. Object 3 is experiencing both of those forces, but they're oppositely directed. Now, the force of attraction towards object 2 is bigger, 2.70, and that means the net force on that object is towards the left. And I took 2.70 and I subtracted off 1.15 and I got 1.55 newtons. That's my net force acting on that object. What does that mean? Well, this raises a question. Are these 3 objects that are charged, are they being held by other forces, right? Is this glued down to some location, you know? Are these things being held in place? Because if they're not, or if they're being held in place, let's say, to do these calculations, and then we let go. So I got these 3 charges, we're holding them in place while we calculate their forces, and then we're going to let go. What's going to happen is, at least initially, object 3 is going to experience a force towards the left. That means it will begin to accelerate. There is a net force on object 3. It will start accelerating in the left direction if we let go of it. If we let go of object 3, it's going to start accelerating in that direction. So again, I'm hoping this all feels kind of familiar. Doing force diagrams, it feels kind of like, yeah, I'm back in Physics 4A and I love these force diagrams. Or the free body diagrams, which we also refer to. So a force diagram, free body diagram, same thing. Ooh, I had mentioned that we're going to be moving on and doing forces in a couple dimensions, and here it is. Here's example number 3. So it's already happened. And now what I've got is objects that are oriented in a way. There's an XY coordinate system we've set up now. And these objects are not along the same axis. So that means that the forces now, based on this coordinate system we're working in terms of, the forces are going to have X and Y components to them. And again, I can kind of hear that out there. People are going, yes, I love these force diagrams. Yes, I love components. So we're going to have to keep track of X and Y components. Now, what it says here is, first of all, let's find out how many charges we actually have. We have 3 charges. We've got charge number 1 over here. It's negative, and it has a magnitude of 86 microcoulombs. Here's charge number 2, right at the origin of our coordinate system. It's positive and has a charge of 50 microcoulombs. Finally, charge number 3. It's also positive, and has a magnitude of 65. So here's a force diagram, or a free body diagram. And they once again are asking, what is the net force on charge 3? Now they're calling it electrostatic force, so they're imagining that these charges are just going to stay held in place as we do the force calculations. So that's fine. So the electric force acting on charge 3 is going to be a combination of two effects. First of all, these two charges are both positive. So the force acting between objects 2 and 3 is going to be repulsive. And as far as object 3 is concerned, that's going to give it a force directly in the positive y direction. So I'll write that in the diagram here. Object 3 will experience a force in the positive y direction because of the presence of charge 2. Now, what about the presence of charge 1? That's also going to have an effect on object 3. Now, charge 1 was negative, and so there's going to be an attractive force pulling charge 3 in the direction of charge 1. So that's what F13 is keeping track of. So F13 is representing a force pulling charge 3, object 3, towards charge 1. Now, this force is going to have components. This force, this vertical force, only had a component in the y direction exclusively, but force 1,3 is going to have components both in the x and the y. So we identified an angle. The angle turned out to be 30 degrees, and the x component is going to pick up a factor of cosine of theta, and the y component is going to pick up a factor of sine theta. Now, once we've identified that, it turns out that the net force on object 3 is going to be a combination of those two forces. So the force that's in the positive y direction plus the force that's tipped. And in order to calculate that, we want to look at the two y components and combine their effect, and then look at the x component and then combine the net effect in the y direction and the net effect in the x direction to get an overall effect. What they're claiming over in this diagram is once we've done that, we're going to get a force off at some angle. Okay. Now, I think I'm going to use theta for this. Let me check and see. I may have angle notation that differs. I do. So sorry about that. But here is our example of using vector addition. And we needed to calculate two force magnitudes. And those come from using k, q1, q2 over distance squared. So the distance between 2 and 3 is 0.30 meters. The distance between 1 and 3 is 0.60 meters. And I put the microcoulombs in here, and everywhere there's a micro, I put in 10 to the minus 6. And what I found was, for force 2,3, the strength, or the magnitude, is 325 newtons. Now, I crossed this one out. I redid this one, I guess. It turned out to be 140 newtons instead. And so, so for force 1,3, I ended up with 140 newtons here. And then, as we were saying, what we want to be able to do is take a look at these two forces and write down